Alright, we're going to look at analyzing some graphs. Our first example here, we have a position versus time graph, and we have a key point of interest here when t is 3. Notice that we don't take on any negative t values. We can't have negative time. So I want you to focus on the first half of this graph where s is decreasing. Okay, so when s is decreasing, that means our velocity is negative. If you were to look at these slopes of the tangent lines, they're all negative there. On the other hand, if we look beyond 3, we can see that our function s is increasing. And if s is increasing, that means our velocity is positive, since, again, velocity is the derivative of our position function s. So the tangent line slopes there, the derivative, it's all positive. Likewise, down here at 3, we have a horizontal tangent line, and that means our velocity is equal to 0. Our position s, it's not increasing or decreasing. All right, the velocity is equal to 0 there. So we can summarize all of this in the form of what we call a sign diagram. So that's going to look like this. So I'm making a sign diagram for velocity, v of t. By the way, we're never going to make a sign diagram for position, s of t. So our velocity sign diagram here, we're tracking what's happening with our velocity. Now, down here on my scale, I've marked off some important t values. T is an important value since, again, we can't have negative time, so we tend to shade over there, indicating it's undefined or irrelevant. To the left of t equals 3, so for values between 0 and 3, we said earlier that this is a negative velocity. That means we're moving to the left. And then at 3, the velocity is 0, so we'll put a 0 there. That means the particle is momentarily at rest. And then from there, the particle is going to be moving forward. So it goes from moving backwards because of the negative velocity to forwards because of the positive velocity. So that means at t equals 3, since the velocity is positive and we have a change in the velocity sign, that means we have a change in direction at t equals 3. Okay, in this example we're given a graph of velocity versus time. So let's look to make a sign diagram for both velocity and acceleration. So if we analyze this velocity graph, we have a key point here at 2. Now above it here, we see that the velocity is positive because it's above the x-axis. At this point where t is 2, that's where the velocity is equal to 0. And then down below here, this is where our velocity is negative. Okay? So above the x-axis, we have a positive velocity. Below the x-axis, we have a negative velocity. Okay? Again, we're given a velocity graph this time. So we can make a sign diagram by marking off these key points. Again, it doesn't make sense to have negative time. We know that when t is 2, the velocity is 0, so I'll put a 0 above that. We have positive velocity to the left and then negative velocity to the right, and that goes on forever since we have an arrow here. So we are talking about a particle that is moving forward, then it stops, it changes directions at t equals 2, and then it moves backwards. So for the acceleration sign diagram, this is also going to have a 0 here. Okay, can't have negative time. Well, with this one, acceleration is the derivative of velocity. So if you're given this line here, if we're talking about a derivative, remember we're talking about a slope of a tangent line or just a slope in general. Well, this line here, it's linear and it's going downhill. The slope is going to be negative forever. So we would have a whole bunch of negatives here. Okay? So, and you can plop down 2 if you want, but if you were to mark 2 off on here, It's not going to make a difference because it's going to be negative everywhere. The signs aren't changing. So suppose we want to figure out where is the particle speeding up and when is it slowing down. So let's first talk about when a particle would be speeding up. Remember we said a particle is going to be speeding up when velocity and acceleration have the same sign. Well, they are both going to be negative for time values greater than 2. Okay, we're not going to include that 2 because up here on our velocity we know that v of 2 was 0. So when the t values are greater than 2, that's when we know this particle will be speeding up. All right, and again, the reason is that acceleration and velocity in this case are both negative. Okay, slowing down we said is where they're going to have opposite signs. Well, that's going to happen between 0 and 2. Okay, in this case, acceleration would be negative and velocity would be positive. And again, just look at our sign diagrams here. Okay, so it would be slowing down between 0 and 2. Okay, in our final example here, this time we are given a graph of acceleration modeling some function versus time. And we don't have an arrow on the end here. It's ending at the t value of 8. So what that means is we can come over here and we can mark this off at 8. Again, we'd have to start at 0 as we talked about before. Now over here at 3, this is a point of interest because we can see from 0 to 3 here our acceleration is negative since it is below the x-axis. And then after 3, between 3 and 8, we can see that it's above the x-axis. So that means that our acceleration is positive. Okay, so on our sign diagram, we'd have a negative, and then we'd have a positive. Now we can't work backwards, at least not yet. We don't know enough math to work backwards and gather any information about velocity. So at this point, we're just going to look at the acceleration sign diagram only. Okay? Oh, and I forgot to add that this point here at 3 is when we have an acceleration of 0, and when we have an acceleration at 0, we have constant velocity. Okay? So anytime the acceleration is 0, we have constant velocity. Again, that's kind of like your cruise control in a car.